Given a reference of a node in a graph with data and a list of neighbors, create a deep copy of the graph. The graph has the following properties. It's undirected, which means the edges of the graph are bidirectional, and it's connected. A path will always exist between any two nodes. In a deep copy, a new instance of every node is created with the same data as in the original graph. Any modifications made to the new graph are not reflected in the original graph. For simplicity, we are creating a graph using an adjacency list where the data of each node is represented by its index in the adjacency list. Each list in the adjacency list describes the set of neighbors of a node in the graph. The index in the adjacency list starts from 1. For example, for this, there are 3 nodes in the graph. So the first node, because of this is in the first position, has neighbors of 2 and 3. Okay, with nodes in the data 2 and 3. This is the second node in the graph, the neighbors of the second node in the graph, and this last one is the neighbors. This last entry is the neighbor. It contains the neighbors of the third node in the graph, and that's what they're trying to explain here. Okay, and you can see that represented visually here. So this is these are the neighbors of the first graph, the second graph, the first node, second node, third node, fourth node. So you can see that 1 is connected to 2 and 4, as you can see here. And then node 2 is connected to nodes 1 and 3. Node 3 is connected to 2 and 4, as you can see. And node 4 is connected to 1 and 3, as you can see here. And you notice that there are no arrows between them. Okay? No arrows between them because they're bidirectional. And from any one node, you can get to any other node, which means they're connected. And I discussed some of these concepts such as bidirectionality and connectedness in the intro video for graphs, so you can feel free to go check that out. And the cloned graph is gonna be cloned like entirely, not by reference. So if you make a change in this graph, it's not gonna affect this. If you make a change in this graph, like update any of the values, it's not gonna affect this. Okay, so that's our goal. And how are we going to do this? They restate the problem here, and then they give the solution block of text. Now, there are different ways to solve this problem. There's a breadth-first approach, there's a depth-first approach. If you're scared of recursion, you want to look up the breadth-first approach to solving this problem. But if you feel fairly comfortable with it, which I don't think anyone should be, right? Because side note, and I've mentioned this in a couple of previous videos, NASA's code standards, code guidelines, they always favor an iterative solution to a recursive solution. So if you worked at NASA and you needed to clone a graph, you would have to use the breadth-first search version, not the depth-first search version of the recursion. But we're going to use that version in this video. Since in this case, it's not too bad, and compared to maybe some of the other like dynamic programming problems we solved historically. And so, yeah, we're going to use depth-first search and create a copy of each node while traversing the graph. We're using a hash map to store each visited node to avoid getting stuck in cycles. Okay, and we do not revisit nodes that exist in the hash map. All right, and you can think of visits as cloning as well, because before you can clone something, you should have visited it. So just it's a side note. The hash map key is a node from the original graph, and its value is the corresponding node in the clone graph. So the key is going to be the original node in our hash map. The value is going to be the cloned node. And in order to solve it, we use a recursive function clone helper that takes 2 arguments, the current node being cloned and a hash map. The hash map, I would say, not a hash map, because we're passing that by reference, because we want every single call of this recursive function to reference the same hash map. And now these are the steps of the recursive function, but there's a step I modified here, so pay close attention. If the graph is empty, return null. Okay, that's just an edge case. And this will also work as a base case for our recursive function. I'm gonna say no. And why is that? So this is our recursive function, clone helper, right? We're passing a node, just like they said, and a hash map. So the current node we're evaluating, we can call it root. And then this is the hash map where we look up whether we've cloned something or not before. Cloned/visited something or not before. So that we don't get stuck in cycles. And this is the first version, the clone function. So we're passing in a node that can be a root node that can be either a node or null. It's just an edge case, really. This is not, isn't our terminating condition for the recursion. And so if the root is null, return null. Otherwise, initialize the map that we're going to use to keep track of the clone nodes. And we're going to recursively call this function, clone helper, and it's defined up here. Okay? Now, we will start from number 2. Create a new node with this, if it's not null, which is our case, create a new node with the same data as the current node and add it to the hash map, right? So we're going to do what we said earlier, create a new node with, and you can read the comments. I think the field of comments are super useful. So we're going to create a new node with the data from what we're passing in, and then we're going to add it to our map that keeps track of things that have been cloned. And the key is going to be the root that we passed in, and the clone node is going to be the value. Next, this loop here is where a lot of the heavy lifting happens in this function. It's not enough to clone a node, right? If the node was connected to other things, the things that are connected to it have to be cloned as well, because you can't connect it to the original things. And I'm going to get back to this statement I just made, but you want to iterate through all the neighbors of the current node. And for each neighbor, check if it's already cloned by looking up the neighbor. If it's not cloned, call the function again, the clone function helper again. Now things just got confusing, I'm sure. But if it's already cloned, this case is fairly easy to intuit. Add the clone neighbor to the new node's neighbors. Then finally return a new node. Okay. Then they give some commentary here, but I think this thing would be useful to look through right now. So this adjacency list is represented by this graph. Now remember, this is the list of neighbors for each node at index starting from 1. So the first entry here is for the first node with data with value 1, and it's connected to 2 and 5, as you can see visually. Let me zoom in to this a bit. Okay, so 1 is connected to 2 and 5. This is node 2 is connected to 1 and 3, as you can see here. Node 3 is over here, it's connected to 2 and 4. 3 is connected to 2 and 4, and so on and so forth. And so this is the visual representation of the graph. And now recursion is really one of the tricks to it is knowing that it's a way of looping through things when you don't know how many things there are. So many looping things, you say for, then you use I, right? For I less than the length of the thing. So when you don't know the length of the thing, which in this case we don't, like in a graph structure, recursion tends to be handy, right? It's a more useful way to iterate through a collection of items. So in this case, every single time we call this function, we clone it and add it to the map. Now we want to check every single one of the neighbors, right? Now these are the original neighbors from the original node, yeah? We want to check if it's been cloned before, because if it's been cloned before, it was set over here. Right, and if it's been cloned before, then this branch won't trigger. This branch will. So if we've cloned this before, we pulled it from here, just add it to the neighbors for this clone graph, because again, this thing is cloned. It got disconnected from all the neighbors for the original node, and so we're creating a connection with the cloned version of the neighbors in here. Now, if it didn't exist within our hash map, the neighbor, this particular neighbor didn't exist within our hash map, what we're going to do, we're going to clone it by calling this function again. Okay? And what does this function do? It does the same thing, right? It clones it, adds it to the list of cloned nodes, and returns the node outside. Once it's done checking all the neighbors, just returns that clone node, because this is where the connection happens, right? We reestablish all the connections here, okay, in this block of code, this loop right here. Because we've already cloned that individual node, but then if you don't have the previous connections, then it's not exactly a complete copy, right, of the original node. So you need to reestablish connections, and that's what this for loop is for. And then it calls itself, but at the end of the day, once the connections are reestablished, you then return that node that has all the necessary connections and the data that we reinitialize here. Okay. So that's what is happening when we recurse through these. And for recursion, before you develop this intuition that I just shared, many times you have to look at a couple of examples. So I recommend some depth research like problems, because they tend to use recursion often, as well as some dynamic programming problems, right? For every iterative solution, many times there is a recursive one. Now, I favor graph problems over dynamic programming problems just because I think they have less complex concepts, not necessarily simple complex concepts, but less complex concepts for you to manage. And so once you do that, once you clone the neighbor that wasn't there before, you then do the same thing you did if you had seen it before. You just make the connection. This is where you make the connection with the cloned neighbor so that it matches 1-for-1 with the original. So it matches 1-for-1. So you don't just clone one. You have to clone not just one, but the connection to two, and not the original two, but the cloned version of two. So that's what's happening in that for loop. And they walk us through it, but I mean, starting from 1, then they clone it, then 2, then they clone it, which it's not a very super graphic, to be honest. Not a very useful graphic. LeetCode's video on this was good as well. But I hope this explanation makes sense to you. All right. So yeah, that's all there is to this problem, really. We can look at the time complexity. It's n plus m, where n is the number of nodes, m is the number of edges. Okay. And then space complexity is O of n, where n is the number of nodes in the dictionary or a hash map. And that's all there is to this. And if you use breadth first search, it's the same time complexity and space complexity. So one isn't faster than the other. But again, it depends on what you prefer. What the goal with this is not so far exactly even like mastering the code for this specific problem, as much as it is to understand breadth first search and depth first search, right? And just be able to adapt that template, because this pattern, it looks like this. Like depth first search almost always looks like this recursive call. I mean, not almost always looks like this recursive call, while breadth first search always looks like breadth first search. They use queues and checking while the queue is not empty and things like that. So watch all these videos, internalize the pattern, the overarching pattern, more than the specific solutions, and you will be good. All right. Thank you so much for watching. See you in the next one.